Is everybody okay? What about you folks on my left? So look, I told you at the beginning, when you play around with the infinite, you better be careful. What seems apparent? See, look at the number line. Like I said earlier, here's the number line. Here's 1, here's 2, sorry, I should start with 0. And in between this, there are an infinite number of rational numbers. Here also infinite number. और ये कितने sparsely, how sparsely they occur, the counting numbers. See that? Yet, they are the same in number. You see that? That's a very deep fact. It's a very, very deep fact. The person who discovered this fact was a German mathematician by the name of Cantor. George Cantor. He was the person who discovered this fact. And Cantor discovered many other things about numbers, their sizes, the sizes of sets. He did some amazing things. And when he started playing with these infinite sets, then people began to ask questions. They didn't believe or accept what Cantor was saying, even though the arguments are so simple. The argument that I just gave you for showing that positive rational numbers and counting numbers are same in number, or the two sets have the same size, is Cantor's argument. It was his argument. Is there any deep mathematics in this? Did you have to use trigonometry? Did you have to use calculus? No, it's simple logic. But the idea is very, very profound. And when Cantor first started espousing these ideas, many mathematicians were very upset. They didn't like it. And they began to criticize Cantor. And Cantor was the inventor of modern set theory. This is what he was doing with sets. He understood that you can assign sizes to sets in terms of the number of elements they have. And then he showed that there is, for every set of no matter what size, no matter how large the infinity, there will be another infinity which is larger than this set. What do I mean by that? So this is a very deep statement. And if I have the time tomorrow and if you have the inclination, we can look at what Cantor did. It was a very simple way. But this is what he said. Right now we looked at two infinite sets. Which are the two? Counting numbers and rational numbers. What did Cantor show? That they both have the same size. The question then arose, are all infinite sets of the same size? What does that mean? That if I take an infinite set, can I put it into one-to-one correspondence with the counting numbers? And Cantor proved, using an argument, that any 10th standard student will, in terms of technical background, easily follow. And he showed that's not true. There are sets which are infinite in number, which can never be put into one-to-one correspondence with counting numbers. So they are larger. They are larger. And that created a furor. But he proved something even more profound than that. He said you take any infinite set, no matter what its size, you can always create another infinite set which is larger than this set. In other words, this new set I create using the old set. I create a new set. And this set, the number of elements here can never be put into correspondence with the smaller, the other original infinite set. So the size of infinity, he said, can always be made larger and larger up to infinity. Now that's something mind-boggling. I don't know if you followed this. So let me explain again very quickly. What did Cantor say? He said, first he showed that rational numbers which look so much larger than counting numbers are actually of the same size as counting numbers. Why? Because you can put them into one-to-one correspondence. And the next question is every infinite set the same size as counting numbers? Rationals are, but is every infinite set? And he immediately proved that's not true. He produced a proof which is so simple which shows that if you take all the numbers between 0 and 1, all the numbers, not just rational numbers, can you give me an example of a number between 0 and 1 which is not rational? Root 2 is greater than 1. How do you make it less than 1? So you subtract from root 2 1.
1 by root 2.
So root 2 is not rational. Okay? Is root 2 minus 1 rational?
No, sir.
Okay, how many of you believe this? I just asked you a statement. You accept, I think everyone is told in school, this is an irrational number. Am I right?
Yes, sir.
So let's assume you know this. Let's not even worry what this means. Now I'm asking you this. You agree root 2 is bigger than 1? Okay.
Yes.
Is this number rational or irrational? Root 2 minus 1. How do you know that? Someone prove it to me. This is easy. How do you prove it? Very easy. Think. Don't be afraid.
एनी रेशनल मतलब जो भी हमें रूट 2 है उसमें चाहे एडिशन हो चाहे मल्टीप्लिकेशन सब्ट्रैक्शन हो वो जो भी रैशनल नंबर वो इरेशनल नंबर ही हो जाता है.
How do you know that? That's what I'm asking. How do you know that? Okay, so let's see. Look. Suppose this is rational. We always prove these things with simple contradiction. Suppose it is rational, it will be of the form P by Q. Am I right? If root 2 minus 1 is P by Q, then what is root 2? It is P by Q plus 1. Now put P by Q plus 1 in the form of P by Q in some way. What will be this? This will be P plus Q upon Q. So this is A upon B, where A is this and B is this. A and B are positive counting numbers. So root 2 becomes rational, but that's a contradiction. So if root 2 is not rational, then root 2 minus 1 is also not rational. And that's a number between 0 and 1. So between 0 and 1, you have lots of rational numbers, but you also have lots of irrational numbers. Here's a simple question. Give me an infinite number of irrational numbers between 0 and 1. I gave you 1. Give me an infinite number. You can do it. You have the idea and the power and the knowledge. I give you 2 minutes. Give me an infinite number of irrational numbers between 0 and 1.
तो रूट 2 में तो माइनस 1 कर दिया ना.
माइनस 1 क्या रूट 1 कुछ भी लिखते जा
सॉल्व करना तो रूट पर सॉल्व कर देगा.
अरे सुन तो रूट 2 में माइनस करना है तुझे 1 1 1 1 1 0 2 1
रूट 2 में क्या माइनस कर रहा है.
हम 1.11 ये भी लिख दें 1.22 ये भी लिख दें. कुछ भी एडिशन करेंगे हम रूट 2 से किसी भी चीज़ से
एडिशन तो करेंगे.
देख एडिशन नहीं कर सकते. मल्टीप्लिकेशन कुछ भी करेंगे रूट 2 से कोई भी नंबर
तो वो बढ़ जाएगा.
फिर बढ़ जाएगा तो क्या होगा. अच्छा 0 का
कुछ भी ऐसे करते हैं. ये तो समझ लीजिए ना वो तो इसमें क्या करता है रूट 2 का 1 से बड़ा जा रहा है
1.414 होता है ऐसा कुछ
414.
Well, the clue should work. Okay, tell me. What do you do? I want an infinite number of irrational numbers between 0 and 1. Tell me. Root 2 divided by?
Root 3.
How do you know that's rational? How do you know that's irrational?
That will be irrational.
He says root 2 divided by root 3 is irrational. How do you know that?
Contradiction. Both are irrational. Contradiction.
How do you know that?
The contradiction.
By contradiction. Well, you have to do it up. Yeah. Either you have the argument or you think about it, right? But I'm not going to spend too much time on this here unless you are clear yourself. So you must come up with a clear argument, okay? So there's a simple clue. Look for simple things. Okay, how about root 2 upon 2? Is this less than 1 or greater than 1?
Less than.
Is it rational or irrational?
Irrational.
How do you know that?
Prove कर देंगे P by
Prove
Q.
it, prove it. Come on, come to the board. Root 2 divided by 2 is equal to root 2.
1 by root 2. 1 by root 2.
1 by root 2.
I asked you for an infinite number. Okay, come on. How do I know that root 2 upon 2 is irrational? 1 upon root 2, I don't know if it's irrational. Do you know that?
सपोज करते हैं ये रेशनल है तो इसे ना रूट 2 इक्वल टू 2p by
1 by root 2 is rational.
Yeah, so simple. अगर root 2 upon 2 rational है तो root 2 भी हो जाएगा rational. That is a contradiction. पे ये तो एक ही irrational number मिला. मैं कह रहा हूँ infinite लो, हुजूर infinite लो. root 2 upon 3 ये क्या होगा? ये क्या है? 1 से कम है? ये rational है कि irrational है? root 2 upon 4.
root 2 by n.
root 2 by n. आज नंदू का होटल चल पड़ा है. root 2 upon n. ये जी हाँ. That's the clue I was trying to tell you. Now this is always irrational. Who will prove this to me? How about you? Can you? I don't know her name. Beta, what's your name? Upasna. Can you prove on the board that root 2 upon n is irrational? Oh, come on, you can. Come, we'll help you. Oh, come to me. Come on. Don't worry. You have it in you. Don't worry. Just go to the board, first erase and take a black pen. Be bold. Erase everything. You can do it. Okay, let's watch Upasana show to us that root 2 upon n is irrational. So you first write root 2 upon n. Now, suppose this is rational. What does it mean? It is equal to it's equal to P upon Q. Where what are P and Q? Positive integers. They are positive integers. Right? If root 2 upon n is rational, it must be equal to P upon Q. Now what we will show is that this will lead us to a contradiction. How? So if this statement is true, then the next statement you write implies, do you know the implication sign? Two parallel lines. Yeah, it is a shorthand. You can write implies as a word, right? Implies. Yeah. Mathematicians are fond of shorthand, but there is nothing there. Don't be afraid of symbols. Implies root 2 is equal to, now can I take n to the right hand side in the above equation? ऊपर वाला जो equation है, where will n go? Equal to n right side में कहाँ जाएगा? Numerator या denominator में? डालो. Equal to np. Please erase. Yeah. Is equal to n times p upon q. Is that correct? You convince yourself. If root 2 upon n is p upon q, then is root 2 equal to np upon q or not? Are you convinced? You are? Okay. Now look at the right hand side. What do you think, beta? np, is that a positive integer? Because n is positive and p is positive, right? And they are both integers. Is q a positive integer? So np is a positive integer, q is a positive integer. So np upon q is a rational number. That means root 2 is a rational number. But that's not true. We know root 2 is not rational. So where did this problem come from? Where are we in the difficulty? Because we assumed that root 2 upon n is a rational number. So that assumption is wrong. And therefore what is root 2 upon n? Irrational. There, you did it. You did it, yes or no? So let's all clap for her. Okay, good. Very nice. So now you get an infinite number of irrational numbers between 0 and 1. So you understand that between 0 and 1 there are an infinite number of rationals and an infinite number of irrationals. You're all convinced about this?
Yes.
Very good. Now here's the interesting part. The irrationals are larger in number than the rationals. Cantor proved it. It's an amazing and simple proof. It's really simple. As simple as what Upasana did on the board right now. Same argument. But people refused to accept that. They began to create trouble for Cantor. And they began to attack his mathematics and his logic. But there is no flaw in the logic here. And Cantor began to suffer. When people attack you, you begin to have some emotional problems. And eventually he had a nervous breakdown. But then he recovered and he did some more very interesting and amazing mathematics. But the attacks continued and he had one or two more breakdowns. Eventually he ended up in an asylum. And that's where he died. And at that time it wasn't clear if Cantor's work is all that great or not, because some very important mathematicians had criticized his work. A very, very great French mathematician who is extraordinary as a mathematician, his name will always be there in mathematics, Poincaré. Poincaré said that this set theory that Cantor has created is a disease which 20th century mathematics will have recovered from. This is one of the greatest mathematicians of all times making a statement. And what is the truth about set theory today? Remember what I told you yesterday? Every single notion in mathematics can be explained with the help of two concepts. Set and
functions.
So was Poincaré right or wrong? In this context, he was not right. Am I making myself clear? That doesn't diminish the greatness of Poincaré, but sometimes we make these errors. It certainly makes Cantor very, very important. And Cantor's work, even though as you can see, none of you are really that well versed in mathematics. I know that most of you have given up mathematics after the 10th grade. And yet, did you have any difficulty following this? I don't believe so. Initially, you may be hesitant, but the logic, the kind of technical arguments are simple. Yet, the work is very profound. This is Cantor's work, and it's very profound. It actually strikes at the very foundation of mathematics. If there is time later, I will explain that to you. But at this point in time, we cease our lecture for today. ये वाला किस्सा फिर कभी. Thank you.
Thank you, sir.